session that will happen later this afternoon. This is a session where abstracts were selected essentially in the field of cardiovascular fluids as well as pediatric cardiology in honor of the legacy of work from Professor Ajit Yoganathan at Georgia Tech and Emory University. So I'll go ahead and introduce the first three speakers. I am moderating this session alongside with Professor Keith Manning, who will introduce the last three speakers. So the first speaker is Milad Samei, who's speaking on behalf of Oda Atum from Michigan Tech. The title of the talk is Flow Dynamic Differences Between Self-Expanding and Balloon-Expandable Transcatheter Aortic Valves.
Yeah, thank you, Dr. Gassi, for the introduction. And as you said, I'm speaking on behalf of Oda because she recently got a full-time job. You can see here. Thank you. So during the last 2 decades, lots of improvements in the transcatheter aortic valve designs. And the materials took place to optimize valve performance and maximize the benefits. Such as replacing stem metals from stainless steel to cobalt chromium to ensure stronger and more efficient anchoring. And also skirts were added to limit the regurgitation, and the valve profiles were altered to allow the minimal interference with the downstream flow, as you can see lots of different types of transcatheter aortic valves in this image. But despite the improvements, the interaction of these transcatheter aortic valves with the flow in the aortic root is associated with non-physiological flow properties compared to the flow in the native animal. So lots of clinical, in vitro, and in silico studies have shown that transcatheter aortic valve performance varies with the following parameters, such as the valve type, namely self-expanding versus balloon-expandable valves, the unique design of the each valve within the same type of group, and the deployment like axial and commissural, and also the surrounding patient-specific anatomy. So from the fluid mechanics point of view, it is important to evaluate the flow downstream of the aortic valve, as it tells us the performance parameters and ultimately the durability of the valve. Also, the turbulence of the flow downstream of the transcatheter aortic valves informs on the pressure drop across the valve and explains some of the reasons behind the differences in pressure recovery among different valves, as it is indicating the difference measurements modalities such as echocardiography and catheterization. So the turbulence in the downstream of the valves also informs us the force that platelets and red blood cells undergo in the context of the general blood damage such as platelet activation, thrombus formation, and hemolysis. So in this study, we aim to characterize the difference in the flow dynamics and pressure recovery downstream of multiple self-expanding and the balloon-expandable transcatheter aortic valves. In this study, the hemodynamic assessment of the small accurate neo 26 mm evolutes and the 23 mm allegra as a self-expanding and the 23 mm safe entry as a balloon-expanding valve was performed in a left heart simulator under pulsatile physiological conditions. So these valve sizes are accepted sizes to treat 20 to 23 mm angles. For this study, the valves were implanted into a rigid test chamber, and the aortic pressure ranged from 80 to 120 mm of mercury. The peak aortic pressure was set as, the peak aortic flow was set at 24 liters per minute, and the heart rate at 60 beats per minute. The fluid used in this experiment was a mixture of water glycerin, which is 60 by 40 by volume, with a property similar to blood. And the valves were placed in the same annulus for all the experiments. So we measured pressures with the Miller catheters as we inserted it along the center line of the aortic valve chamber and recording the pressure at every axial location along the ascending aorta with intervals of 5 millimeters downstream of the valve and 1 millimeter inside the valve. So as you can see, position 0 corresponds to the most upstream measurement, which is the ventricular pressure, and the position 1 to 3 millimeter corresponds to the last measurement point. And we call it recovery region. So we recorded 50 consecutive cardiac cycles of the aortic pressure, ventricular pressure, and the flow rate at a sampling rate of 100 Hz at every measurement location. And the mean transvalvular pressure gradient, which we call it PG, is defined as the average of the positive pressure difference between the ventricular and the aortic pressure curve during the forward flow. And the pressure recovery calculated from the difference between the peak pressure gradient, PG maximum, and the net pressure gradient, which is the recovery pressure. We also recorded a high-speed recording of an NFAS view of valve opening and closing at a frame rate of 1000 Hz. We also did a particle image velocimetry where we performed to assess the flow downstream of the valves. The flow was seeded with fluorescent particles with an average diameter of 10 microns, and the time series recording was acquired at the temporal resolution of 500 Hz, and the phase lock recording it for the sake of statistics. So from the NFAS images, we calculated the pin filling index using this equation where L actual represents the deflected free edge of the leaflet, and L ideal represents the unconstrained free edge of the leaflet. The Reynolds shear stress was calculated from the phase lock recording, which is an established metric to evaluate turbulence and any associated blood damage potential, and is calculated using this equation, where rho is the blood density and U prime and V prime are instantaneous velocity fluctuation in the X and Y direction. In addition, viscous shear stress was also computed from this equation to evaluate the actual shear force per unit area that experienced by blood element. So let's look at the NFAS view of each valve, which gives us a valuable information. The first one is a 26 millimeter evolute. You can see some level of fluctuation in leaflet fluttering, and we measured the pin filling index as 3.9%. So the second one is the Sapien, which shows a very low level of fluctuation, but with higher pin filling index, which is 6.7%, which was the highest in all four. Now look at the accurate node, and you can see a high level of fluctuation. And I will show you in the next slide that how it contributes to the statistics. And the pin filling index 2.8, and then the Allegra, you can see a big geometric orifice area, very low leaflet fluctuation. So from the PIV, this figure shows the average flow velocity downstream of each valve at acceleration, peak systole, and deceleration phases. And you can see the dark streak of red and blue vorticity contours, which represent the shear layers corresponding to the jet boundaries, and the distance between them represent the width of the jet. As the flow starts accelerating, reaches the tip of the fully open valve leaflet, it separates from the leaflet tips and travels as a free shear layer that is a region of concentrated velocity as an indicator of the flow rotation. So comparing between each valve, significant differences were found, except between the Sapien tree and Allegra. And this figure shows the principal Reynolds shear stress at different phases in the cardiac cycle. The maximum Reynolds shear stress occurs in the peak systole, as we expected. Then the dark blue patches indicate the high level of Reynolds shear stress. And Allegra had the smallest level of Reynolds shear stress, and Accurate had the highest. And looking at these two NFAS images I showed you, you can tell that because of the leaflet fluttering, it gives us a very high level of Reynolds shear stress. So to quantify the Reynolds shear stress distribution more accurately, this figure shows the probability density functions of Reynolds shear stress for each of the valve at peak systole. The accurate nil and the evolute R, which are the blue and the red curves, present the largest distribution of Reynolds shear stress. The Allegra shows the minimal range of Reynolds shear stress, which is up to 320 pascals, and followed by evolute, which is 600 pascal, and then accurate and sapien. And in the literature, it reported that any value exceed 100 pascal can be associated with the blood damages. And the sapien tree, accurate neo and Allegra shows equal distribution for those Reynolds shear stress less than 100 pascal. But the evolute shows higher values. And to evaluate the actual shear per unit of area that is experienced by blood elements, we calculated the instantaneous viscous shear stress for each of the flow. And all the instantaneous viscous shear stress magnitude obtained were lower than 10 pascal, which is the threshold associated with the potential blood damage. Our last result is you can see the left shows the variations of pressure gradients along the aortic route with 4 valves, and the right one is the standard deviations of it. The results are plotted from the ventricle side upstream of the valve to the downstream side, up until the end of the aortic testing chamber, which is 120 millimeters. As the flow accelerates the valve, the pressure gradient decreases from the ventricle side to the aortic and reaches minimum at vena contracta. After that, it recovers, and this is what we expected from these curves. So first of all, we can see the location of the vena contracta, which is the minimum value, are not equal to for all valves. The peak pressure gradient was highest with the accurate neo. The recovery, which is at 20 millimeter, the smallest pressure gradient obtained with the Allegra, and the largest pressure recovery was obtained with the accurate neo, and the smallest with the evolute. And from the right figure, we can notice that the fluctuations of the standard deviations are higher with all the self-expanding valves because of the stem frame compared with the sapien tree. And the importance of accounting for pressure recovery is that it gives us the true pressure gradient across each transcatheter aortic valves, and accordingly a more accurate assessment of the performance of the valve. In conclusion, the hemodynamics downstream of 4 transcatheter aortic valves, in which 3 of them were self-expandable valve, the evolute, accurate, and the Allegra, and 1 bone expandable valve, which was the sapien tree, were evaluated in study in vitro pulsatile condition. And there was a distinct trend of performance obtained with each valve, independent of whether they are self-expandable or bone expandable. The Allegra valve, which is a self-expanding, and the sapien tree, which is a bone expanding, were characterized by the lowest leaflet flutter, and thus the lowest turbulence downstream. And I would like to thank our collaborators. This is the lab group photo. All of us not here, but this is the best one. Thank you.
1 minute for questions.
Interesting talk, first of all. The question I have is for the valves that we have, the thickness of the same or
No, some of them were bovine, some of them were porcine. So the porcines were thinner. So it might be one of the reasons that you have more fluctuations in the porcine valves. For example, sapien is bovine, has less fluctuation. Might be one of the reasons. It's thicker.
And all material coverage the same or
No, almost, but I think bovine is more rigid, right?
Yeah, the line is thicker.
Thicker and rigid. Dr.
Meanwhile, can you put the first slide with the baby?
Oh. I answered
John, that was my
Yes.
question about the leaflet days.
Oh.
So, you define blood damage very broadly in one of your other slides, but in some of the results,
I think it refers to the analysis. I'm not sure about control yet.
Let's thank our speaker. So our next speaker is Dr. Kerem Teknik. He is going to be presenting a novel biventricular mechanical support configurations for the failed spontaneous circulation. And Kerem's from the KOC University.
Hello everyone, actually I'm very excited to talk in this special session because it has been 20 years ago I was a rocket engineer working on very funny combustion systems, and Dr. White actually gave me a chance to work on the biophysics field, and then it was a very long adventure working and we had a chance to have children with heart defects. And especially this talk also shows the impact of his research, global impact, because this is performed in Istanbul with several surgeons and clinicians in my lab, and for the single ventricle patients. Actually, this is the only talk in the session about congenital heart defects where Dr. Zwei's research is all about. And these slides actually originally from his slides, where you see there's a normal ventricle and a single ventricle with a hole in between the ventricles where there is mixing of blood flow, and there are very different kind of these defects. And the only way to survive these patients is to do a series of surgeries, and the last stage is actually the Fontan surgery, where we have a single ventricle. And this surgical strategy actually evolved over the years, as many of you in the audience know, and we currently have modern designs of this system. But whatever we do, actually we cannot get rid of these complications, especially on the GI system disorders and like thromboembolism, arrhythmias, and these are all related, most of them are related to the high venous pressure on the right side of the heart. And one way actually to solve this paradox, we call Fontan paradox, is with ventricular assist devices or mechanical support on the right side. We call these Fontan assist devices, not ventricular assist devices. They are a bit different. And there are many of these different versions. One of the drawbacks is the pulsatility. We cannot provide the physiological pulsatility on the right side, so the lung arterial system is not very happy with these devices, and we actually introduce more and more problems to the system. Now this is one of the devices introduced in my group. Actually I took this video for Dr. White. This is the surgery we performed with the pediatric surgeon. Actually she's a very good surgeon. We are trying to test this turbine and the pump. This doesn't have a motor, and this is from our first operation with the sheep. So in this talk I will actually introduce you another ventricular assist device option for the Fontan patient, and this idea is actually inspired from the Ross operation. As you know, we actually use the right pulmonic valve on the left side, and we introduce a mechanical heart valve on the right side. And we don't basically throw away the pulmonic valve. And this actually gave us an inspiration. So why don't we actually use the single ventricle, especially for the failed Fontan patients? There is actually, they need a transplant. And there's a period of transplant, there's a bridge to transplantation. And during that time, we can actually use the single ventricle instead of putting to the system many mechanical devices. So actually, we want to develop a novel Fontan failure support strategy where we have a native single ventricle is spared and used in the right side to support the pulsatility. And in the left side, we actually want to use a standard left ventricular assist device where it is very well established on the left side of the circulation system. And we test this concept in two main single ventricle failure modes. Over the years, we learned that there are actually two modes of Fontan failure. One of them is due to the systemic failure, the other one is due to the pulmonary, high pulmonary vascular resistance failure. And we studied this in both systems. So this is a conventional left ventricle support for a systemic ventricle patient, where you put a ventricular assist device from the apex to the aorta. Our configuration is to use the LVAD on the right side, on the left side again, but use the single ventricle on the right side. So we have a biventricle circulation system. Of course, this is very challenging to do surgically, but there are actually motivated surgeons, and that actually introduce an economical approach also for some patients that are waiting for the transplants. Again, as I told you, the pulsatility also has a potential to heal the Fontan right-sided circulation, the physiological effects. So to study this, we have an ideal Fontan circulation state, and this is the first Fontan failure mode. The Fontan failure mode has two stages. First one is the acute failure stage, just after introducing a failure on the systemic ventricle, and there is the chronic phase, so there are some changes in the circulation system between these two stages. Also, we have this VD-CMS, this conventional mechanical support for LVAD, with an LVAD, and there are these circuits also you can follow these, where we have a pump on the left side. And the switch is basically we put the single ventricle to the right side, and we use the pump as a left ventricle support system. In the second Fontan failure mode, we actually have high pulmonary vascular resistance. Again, we have acute and chronic phases of this failure mode. Here, the conventional support strategy is used right ventricle assist device. And again, we actually use the switch operation again for this failure mode also. Here we also wanted to test some very severe failure of the ventricle that has a tachycardia and also bending of the outflow tract of the ventricle. Okay, so we have more severe versions of the failure mode. So we studied this with our established lung parameter model, and it's been developed again since 2005 for Fontan patients. We are getting actually very good PV loops with this system, and we have actually a digital twin of an idealized Fontan patient. This is like an average of many studies and literature data and listening. So here we do both computational work and also in vitro work on the mock-up system. We actually created a very complex experiment which starts with the ventricle dysfunction state. We actually have a ventricle assist device, conventional Fontan support for the failure, and we actually created the switch operation. So for the honor of Dr. Ryan, we have all these complex in vitro tests in the lab. And you see here we have clamps, and we don't change anything between these stages because we have to compare them from each other. So we put clamps and we remove some of the pipes, and we have the system actually goes very smoothly from one stage to other, and we get the data for that. We generally in the field don't compare lab parameter models with the in vitro data, and this time we actually had a chance to compare or validate our lab parameter model with in vitro tests. Again, this is the team that Dr. Y actually started. We have to compare all the computational results with in vitro tests. And you see they are fairly good. In the systemic side, we have some high errors, but again, these are explain these also, but we got fairly good agreement for all these stages with the in vitro or computational simulations. I think this is one of the few studies we have a lung parameter comparison with the in vitro tests. I also interested about, actually one of the reviewers asked the effect of inertance because our lung parameter model didn't have this inertance effect. So actually we neglected this traditionally because these are pediatric circuits and neonatal circuits. The pipes are small. But actually we also calculated the effect of inertance on pressure drop for this circulation system. And on the aortic side it is around 4%. On the right side it is even lower, 10 to the minus 3. So the inertance is very low. And also we have very small phase length between the flow and pressure in the measurements. So the inertance is really less important. So here some of the waveforms we compare with computations and experiments for different cases that we studied. And this is the proposed configuration VD switch. We have some oscillations because in the in vitro test at the exit of the ventricle assist device there is a pressure transducer which actually pick up signals from our in vitro system. Okay? So I think the time is coming. To take the story short, when we put the failed ventricle to the right side, it provided good possibility, especially for the systemic failure case, and we actually able to get almost very close to the biventricular circulation for the patients. Also the waveforms are shown. For the PVR case, where the high pulmonary vascular resistance case, we really need a severely failed single ventricle to work on the right side, because even this single ventricle, when you have a high PVR, it created a lot of pressure on the right side, and it didn't really fit for that case. But if you have a really severely failing patient, that can also be done for that case. And again, the pulsatility levels is same as the biventricular normal circulation levels, which is actually very good. So this is summary. Again, I'm skipping this. One thing I want to highlight is we really need animal experiments for this to verify this concept. And I thank for European Research Council. They are supporting me with a lot of projects, 3 of the ERC projects I got, and also my institute, Koç University, for the support. Thank you very much for this.
Two quick questions.
Do you have any planning, any vivo studies?
This system, yeah, if we can do an animal experiment, yeah. The surgeon is very, he wants to do it on the human, but I'm usually pulling them.
Do you envision this to be completely implantable? So it's like a bridge to transplant?
It is definitely a bridge to transplant. I think, but for a long time, so it will also have to recover the venous side, so the compliance can actually come to the lower levels, normal levels in with this system. And then we will not throw the single ventricle, because we love the single ventricle also.
The station would still go through the lung stage?
This is the last stage of the Fontaine patients, the failure stage.
So you're not concerned with how the lungs might have remodeled during the Lent period?
Yeah, as we all know, all Fontaine eventually come to this stage, the transplant stage, and that actually fits well for this case.
So let's thank Karen, can you go to the USB direction? So let's introduce our next speaker. So our next speaker is Dr. Zara Mohamed from McMaster University. She will be presenting the interplay between transcatheter aortic valve replacement complications and coronary artery disease. So please welcome Zara.
Thank you very much. Hello everyone. So I try actually to present the slides of my PhD students. They couldn't attend because of lengthy, US visa, but so I try actually to convey the message. So actually, he started working, on transcatheter aortic valve replacement for 2 years, and then, the first 2 years, and then from 1 year ago, he switched to understand the interplay between paravalvular leakage and coronary arteries following transcatheter aortic valve. So I think all of you know that almost 50% of patients with transcatheter aortic valve replacement has coronary artery disease. And then, a good population of them also, they have paravalvular leakage. So I expect that it will be decreased by the time because younger patients also join, for transcatheter aortic valve replacement. But for now, 50% of them has coronary artery disease. So simply the objective is to investigate the effect of TAVR complications, specifically paravalvular leakage for this specific, presentation on coronary arteries. So for this, we developed, a patient-specific, long parameter algorithm and fluid solid interaction. So the first one, I myself started, my first year of PhD developing a long parameter algorithm. From 5 years ago, I decided to make it, really patient-specific because it was not patient-specific, it was for hypothetical cases. So, and then we are really interested on doctor base because of that is not non-invasive. So I developed a long parameter algorithm that can cover ventricular disease, left side, valvular disease, a part of vascular diseases. And recently, my students actually developed that further, and also we added coronary. So an interesting thing about that long parameter algorithm that is truly doctor-based. We need 5 to 8 input parameters from Doppler echocardiography machines. All of them can be measured reliably. We changed the algorithm several times because we realized when we talked to the cardiologists that the input parameters that we considered for the algorithm, we cannot measure them reliably. So now, I think we are fine, with the diseases that we are working. So recently added the coronary. So that long parameter model can stand alone and can actually calculate global hemodynamics, left ventricular function, and also. So the backend also use the long parameter model and then do actually FSI, So the long parameter algorithm, it's not fully coupled to the FSI yet. We are using, flow and pressure because as you see, we need flow and pressure, everywhere. So for inlet, for ascending aorta, some information from left ventricle, some information from coronary. So he actually used the long parameter algorithm and then get those information and apply for that one. So he actually wanted to present only for 2 patients today, but he did for 6 patients and he's continuing to do it for 35 to 40 patients. We received data and would like to have a stronger clinical messages. So patient 1, as you see, just showing vertical structure and also a stagnation region. That as you see when we have paravalvular leakage, the aortic root vortices will not favor the transfer of blood flow to bar ostium in the aortic root, which is not the case when we do not have paravalvular leakage. And also a stagnation, as you see, is only for patient number 1, but you see that this is not, it's major, it's not trivial, and you can see a stagnation, differently. So far we didn't realize if we can say that usually one leaflet, has more, for example, stagnation, but we continue to understand that one better. The other thing, he continued actually to explore local hemodynamics for coronary, as you see, pre-intervention and post-intervention. So the premise, as you know, endothelial cells are exposed, if they are exposed to low wall shear cells, display a associated with back progression. So that's the reason that he tried to, post-process the data and find, the bone shear stress pre and post. So if you see, it's significantly reduced, post-intervention, which is not really good, because of progression. And also he continued actually investigate local hemodynamics now about aortic root. So look at the magnitude is actually more informative. Maximum time average of bone shear stress pre-intervention and post-intervention, it's much higher, and we didn't find a cutoff threshold, but based on what we learned from the literature, very high bone shear stress, typically higher than 3 Pascal, could contribute to tissue rupture. We are thinking this is major, if that patient wanted to use, and then parameter leakage that we investigated, none of them were severe. They are mild or mild to moderate. So I just wanted to say that we didn't, explain that information, but none of them is severe parameter leakage. It's actually the cases that usually, the cardiologists watch out the patient, and then the data are very new. So they are for 2020 or 2021. That we have new transcatheter aortic valve in place, and then paravalvular leakage actually is significantly low. The other one is global hemodynamics that we are getting only from non-parameter model. It's very interesting for us, that I think also for our cardiology collaborator, that as you see the left ventricle load significantly increasing both of them. So if you look at pressure, so there are pressure gradient pre-TAVR for sure, but post-TAVR, yes, and that's fixed. That clinicians usually look at that information, that you don't have any pressure gradient. But look at the load. So the load is significantly higher. Patient number 1 is low flow. Patient 2 is not, but both of them, it's much higher. Think about that this is only for one cardiac cycle. Think about 1 minute, think about hours, think about months. So this is like, this is really a disaster. The other one actually is flow rate through actually coronary. So it decreased, significantly in majority of them. And as you know, inadequate coronary flow rate, and so could lead to worsening the heart failure. This is also another thing that we realized in 5 patients that we did so far. So if I wanted to summarize what happened within that 5 patients that we did so far, paravalvular leakage limits the benefit of TAVR, restricts coronary perfusion due to the lack of sufficient coronary blood flow. Paravalvular leakage may increase the left ventricular load, and actually it increases the left ventricular load for all cases that we have. It's not only for paravalvular leakage, because I understand that for some of them, after intervention, we have higher, stroke volume. This could be another reason, but paravalvular leakage is the dominant factor. But there are other reasons, that the left ventricular load actually is higher. Paravalvular leakage decreases the coronary wall shear stress that can promote atherosclerosis development, and also can increase wall shear stress at the aortic root that can cause rupture. So, we hope that we can, continue, and then maybe next time can, present, Bani can present, more mature information. But thank you very much. Thanks a lot.
How did you change your counter teaming out? And second one, have you measured the residence time of particles of the science? Have you considered it?
So he did, yes. But for non-parameter model, I can answer you more precisely because this is my own contribution. But for the second one, yes, he did, and we can contact Ajit and share information. But yes, for non-parameter model, they are 5, 7 information. So initially we generated based on any information from aortic valve, mitral valve. But now we are getting information only from aortic valve. From mitral valve, we need just qualitative data, and also we need the stroke volume. So the thing that non-parameter is really, really sensitive is the stroke volume. And as you know, we have 3 different ways to calculate the stroke volume. I'm using Dr. Cooper. One of them works better for us. But 5 to 7 input parameters, aortic valve, and also brachial pressure, and also stroke volume. And the rest, we are tuning the system using systematic resistance and systematic compliance, using optimization algorithm. And also we did your validation with the catheter. Not for coronary, you couldn't find any information, but before that we tried to validate it.
Thank you.
More questions? Just a follow-up question on the voluntary. I was wondering the image that you use for the simulation. So what are the things that have from Doppler or catheter?
From Doppler, only from Doppler. We are not using any information from catheter, but we validated. We don't have in vitro data, so we bypass and we use in vivo data. So we are not using any information from cardiac catheterization. We are only using Doppler echocardiography data. For coronary, we had a hard time because for many populations that we received, we could just get those information because we need coronary dimension at the beginning. But we did some tests under control, some people that we can, but everything is from Doppler echocardiography, all of them. None of them coming from cardiac catheterization or CT or MRI. It's just only Doppler.
Sorry, so for flow quantification, what do you use?
For 3 dimensions, so yes, this is another thing. But for non-parameter,
Sorry, for flow, in that flow, you have a waveform.
yes, waveform, exactly.
That comes from the MRI.
That's come from Doppler-based non-parameter model, but the geometry obviously we reconstructed using CT data, so it's something else. But non-model is Doppler-based. That can stand alone, but also we are using, the boundary condition that we are using, the levels we came from non-parameter.
Just a quick question. Is that the FSI or just a region?
It's FSI, but some parts he did simplify. He did FSI everywhere, and then he actually simplified, some part of the region, and then he compared. So it's not completely FSI everywhere. So I am sorry that we couldn't, get more information, but we can discuss after.
Right, so let's thank our speakers.
We'll be spending on predicting valve performance using logistic regression from the lab.
so hello everyone, and thank you for coming. My name is Brennan Vogel. I'm a PhD student at Dr. Katoom's lab at Michigan Tech. Today I'll be presenting on predicting valve performance using logistic regression. So for a little bit of background, aortic stenosis is is the major cause of mortality amongst heart valve diseases, and its prevalence is increasing with an ever-aging population. Currently, the most efficient therapeutic option for severe aortic stenosis is the replacement of the diseased valve with a bioprosthetic valve. The performance of these bioprosthetic valves differs from patient to patient, which makes it very difficult to predict their outcomes on an individual basis. Despite the attempts of several studies to predict valve performance, a simple, easy to use, easy to visualize, and easy to translate to clinic model that can numerically estimate the probability of valve performance failure and allow the comparison among different possible valves is still lacking. Therefore, our aim in this study was to develop a data-driven statistical model that predicts the probability of failure for a surgical and transcatheter aortic valve based on different physiological parameters. To do this, we started by collecting training data using experimental data. And we then applied a predictive model on that data, which resulted in a formula that shows us the probability of valve failure. So I'd like to also take a moment to emphasize that this study was done exclusively on experimental data, just as a proof of concept, but we do intend to develop another model using clinical data in the future as well. Okay, so step one was generating our input training data. And to do this, we hemodynamically assessed a surgical 25mm magnet use valve, which also has an internal diameter of 22 millimeters, as well as a 23mm SAPIEN 3 transcatheter valve. This was done using a pulse duplicating left heart flow simulator. And so we had different experimental conditions that we used. You can see them on the table on the right. So we had different blood pressure conditions where we varied the systolic blood pressure or the diastolic blood pressure. And we also had different heart rates as well. But the cardiac output remained at 5 liters per minute for the entire study. So, and for each experimental condition, we also recorded a total of 30 cardiac cycles, which resulted in a total of 1,924 different data points to be used in the model. Okay, so then the next part of this was generating our output parameters. So the performance of an aortic valve is affected by the output being greater or lower than a threshold, such as the stenosis criteria for transvalvular pressure gradient. So for such cases, the performance of the valve can be enumerated by a binary output or a binary event, so either a 0 or a 1, where 1 indicates the event of failure and 0 indicates the event of survival. For example, the recommendation of the echocardiographic assessment of aortic valve stenosis defines mild aortic stenosis as greater than a DP greater than 20 millimeters of mercury. So therefore, in our study, any values of DP that are greater than 20 millimeters of mercury indicate a failure event of the valve, so a binary value is 1, whereas any values less than 20 millimeters of mercury indicate a survival event in the valve, so a binary value is 0. So for such binary events, when we have enough experimental or empirical data available, a logistic regression model can be employed to estimate the probability of failure as a function of the hemodynamic condition. So then our next step was generating our logistic regression model. To do this, we used the formula, the first formula that you see there. And so P is the probability of exceedance, and then L is called which can be expressed by that second equation that you see there, where A sub I is the regression coefficient, and X, Y are the input parameters to the logistic regression, and then N is the number of input parameters. So I'll go over this a little bit more in the next slide here. So here we're seeing the employed logistic regression model, which takes the form shown in the equation there, which is our probability of DP greater than 20 millimeters of mercury, based off of heart rate, systolic blood pressure, and diastolic blood pressure, so the experimental variations that I showed earlier. So A sub naught through A sub 3 are the regression coefficients for the linear non-odd, and we can see the values that are associated with those that are shown, along with their corresponding p-values. So any p-value that was less than 0.05 is considered as significant, and you can see that all of them for both valves were significant. So that just shows that our experimental parameters that we're using, so heart rate, systolic blood pressure, and diastolic blood pressure, all contribute to determining the probability of are each at different diastolic blood pressure. So the two main takeaways from this are, as we're increasing that systolic and diastolic blood pressure, we're seeing that our probability of failure in the valve is increasing. And then if you also notice, there's conditions here that weren't actually present in the training data. So for example, a blood pressure of 110/70 wasn't present in the data. So it allows us to, the model allows us to interpolate what the probability of failure would be at these blood pressure conditions. So then in this slide, very similar to the last, we're looking at the logistic regression plot for the SB3, again at 60 beats per minute in our 3D and 2D format. So again, just taking a look at that 2D format, right away you can see that the distance between those diastolic blood pressure lines is a lot more significant than we saw in the magnitudes. Okay, so now I'd like to walk you through how we can use this model to help with risk-informed decision making. So first we'll take a look at case A, which has a blood pressure of 130/80 millimeters of mercury. So what valve should we use? Well, we can input our pressure data into the model, and then we can see that we have a probability of a valve developing pressure gradient over 20 for the magnet E's at 7%, and then 42% for the sapien 3. So our clear choice here should be the magnet E's. Now we can take a look at another case, case B, which has a blood pressure of 110/80 millimeters of mercury. Again, what valve should we use? And similarly, we can just input that pressure data. You can see here now that the magnet E's has a probability of failure of 3%, whereas the sapien 3 is at 19%. Kind of the key takeaway here is that when we're changing the systolic and diastolic blood pressures, that we are seeing a change in the probability of failure. And then more specifically, looking at that sapien 3, like I mentioned in the last slide, we saw the distance between the diastolic blood pressure curves is a lot more, and you can see it here as well. So that's why we're seeing such a drastic change between the probability of failure between these two cases here, the sapien 3 specifically. Okay, so then next we're looking at testing the accuracy of the model. To do this, we use a confusion matrix, which has the components that are shown there. So true ones were the number of failures that were correctly identified, and true zeros were the number of survivals that were correctly identified, and then false ones were the number of failures that were incorrectly identified, and false zeros the number of survivals that were incorrectly identified. So a logistic regression model that results in more true ones and true zeros, and less false ones and false zeros as well. So here we're showing our receiver operation characteristics curve for the logistic regression models. And the line there is, on the y-axis we're plotting sensitivity, and then on the x-axis is specificity. So kind of the key thing that we're looking at here is that area under the curve that shows the AUC. Both valves in this model, or in this study, had AUCs greater than 90%. And so just a little bit more information on this AUC value. So an area under the curve of 0.5 corresponds to a random level, where the output is independent of the input, whereas an AUC of 1 corresponds to a perfect level, so 100% accuracy. And then an AUC that's less than 0.5 indicates that the logistic model is performing worse than a random level. And again, in our study, we were above 90%, which is really good, so it shows that we have a good fit for our data. And then finally, we look to validate our model. And to do this, we added an additional experiment using blood pressure conditions that weren't present in the original training data. So going back to case A and case B, both of these values weren't present in the original data. So we tested two new experiments at 130/80 and 110/80 millimeters of mercury. And then we individually counted for a total of 57 cardiac cycles the amount of times that that DP was above 20 millimeters of mercury, or it was below 20 millimeters of mercury. And so this allowed us to manually calculate the probability of failure compared to the probability of failure using the logistic regression model. So if we take a look here for the calculated DP range from this additional experiment, we see the magnet E's has the probability of failure of 0%, the sapien 3 of 37%. So if we compare that to the prediction from the model itself, we see 7% from magnet E's and then 42% again from the sapien 3. So close agreement between our additional experiment and the model itself. And then we can take a look at case B as well. For both valves in the calculated range, we were at 0% probability of failure. So that just means that in the 57 total cardiac cycles that we had, there was none that actually exceeded the GP of 20 millimeters per mercury. So if we compare that to what was shown in the model, we see 3% for the manganese versus 0%, fairly close. There's a little bit of discrepancy there between the sapien 3 values, but we can improve the model just by adding more data points in the future. And then finally, so going back to the AUC, we saw that we had values greater than 90% for both valves. So that pretty much showed us that this preliminary model offers a good fit to our presented data. And then, so at the moment, like I mentioned earlier, this work is just a proof of concept on valve reliability in an in vitro environment without accounting for several variations that we see and then we're not also accounting for any pre-existing conditions that a patient might have that would limit them from receiving a transcatheter valve. But our overarching aim is to apply this model on clinical data in the future once we've received our necessary data. So once again, thank you for all for coming and taking my questions.
Very interesting study. But the one thing I was thinking about is, so you're using the blood pressure as predictors. How would you get that in clinical context? Like how would you know what the post-implant blood pressure is going to be?
So they will measure after the valve replacement. So either invasively or non-invasively. So non-invasively would be echocardiography, invasively.
Oh, I thought you were trying to figure out if the valve's going to fail before you.
So yeah, it's kind of the idea, and for clinical data specifically, it would be looking at patient characteristics. So kind of the idea is we want to have this like a based application, like something like the CHAD-VAS score, if you're familiar with that, where clinicians can input a bunch of the patient parameters before the surgery, and then it'll output whether the valve, like what the performance of the valve is going to be essentially. So if, when we actually use clinical data, it'll be a little bit different, but this is just to show that the predictive model does work.
So EP is transient valve, right? And your time for failure, or is time?
So when we're doing the, I guess why we're using statistical model here instead of something like AI or any more complex tools is that, so like we see variations between each cardiac cycle, right? So it's never going to be, if we say cycle 1 is 18 millimeters of mercury, and then cycle 2 isn't always going to be 18 millimeters of mercury. So time does play a factor into this, and it's just something that we have to consider in the future.
There's the time for the transient, but there's the time failure, right?
Yeah.
Hopefully what
That's also part of it. We have reviewers that have asked a similar question because they're talking about how the valve can kind of shift as it's after it's being implanted, which might result in different pressure gradients afterwards. And that's just something we'll continue to do.
He'll be presenting on hemodynamic impact of anterior leaflet laceration and transcatheter mitral valve replacement. Dr. Zinn. Thank you.
All right, thanks a lot. I am presenting the work of Keshav Kohli, who was a PhD student who just finished, and he was co-advised by myself and Dr. Yoganathan. So, mitral valve disease is very prevalent in the United States and all over the world, actually, and very poor prognosis and very poor quality of life if it's untreated. So really the standard for treating mitral valve disease is surgical repair replacement. The difficulty is that about 1/2 of the patients who should get a valve will not be operated on by the surgeons because of either advanced age or comorbidities, so they're turned down for surgery. So there's been a lot of work with, like, what are we going to do with these other 50% of the people to treat their mitral regurgitation. So one thing that you could do is you could do transcatheter mitral valve replacement, or does this look like? So this is actually the Tendyne valve, which is now owned by Abbott, and it's deployed in a transapical approach, but this can also be done in a standard catheter approach with the Edwards sapient valve, which you know is more normally used for the aortic position, but it could be put in the mitral position. So now we have this possible treatment. So what are the complications of this? So the biggest complication by far is something called left ventricular outflow tract obstruction, and it is just like what it sounds like. If we put this valve in this location here, if I look at this cartoon of the left ventricle, we do not get rid of the native mitral valve leaflet. So this anterior leaflet is displaced and pushed in to the left ventricular outflow tract. So if the patient has, for example, some subaortic stenosis or a different angle of the aorta, you can almost completely obliterate this left ventricular outflow tract with this procedure, or you can cause a pressure gradient, right, that was not there before. So the reported incidence of this is up to 40% in people with highly calcific mitral valves. And you look at that second line there, 62% in hospital mortality. So it is a absolutely tragic event if this happens. So this is what people are screened for, whether they can get the procedure or not. And it turns out that, of course, people are picking a very conservative screening criteria because they don't want the 62% in hospital mortality. So about 1/3 of the patients who should get this procedure now can't get it. Okay? So what can we do about that? Well, let me just take one step back and show you sort of how this is done, because it's going to be important as we go forward. So how would they screen these people? So they get a contrast-enhanced dynamic cardiac CT, and then you reformat that, and then you put a virtual device in it. So, right, you have either a CAD file from the company or a micro CT of the valve, and you put it in there, and you take a look, and you say, how big is that mitral valve? How big is that left ventricular outflow tract? So if it's below a certain threshold value, then you say that's going to cause a gradient based on previous studies, so we want to stay away from those people. So that's the 30% of the people they don't have a big enough neo-LVOT, they call it, so the LVOT after this device is put in. Okay, so is there anything we can do that to mitigate that in any way? So one of the things that has come up with is something called the lampoon, okay, and it's basically lacerating that anterior leaflet to prevent left ventricular outflow obstruction. Okay, so we're basically going to cut this thing with an electrosurgical catheter, so it's still not an open surgery, but we're going to cut through it. So then you see when they do this lampoon, now there's open spaces, right, for the valve that's opened up and not in the other one. So there's actually a little bit more room for flow. So this is just a picture. So the left anterior leaflet displayed. So now there are cells exposed. So the flow can now go through those cells, whereas before it had to go around the valve. Okay. So the idea is that if this could be, you know, a way to get these people who failed in screening into this treatment. So that brings us to our motivation. So lampoon is becoming more popular as a tool to expand the patient population who can get TMVR. However, there's no way to really quantitatively know the effect of this procedure, right? So a group of interventional cardiologists got together and said this should work, and then they did it, and they did it in some people and it worked, but there's no way to do a control study, right? You can't say, you people who failed, go and get this valve, and you have a 62% chance of dying in the hospital, and we're not going to do anything for you. So you can't do the control study. Okay? So there's no way to do that. So what we're going to try to do is reverse engineer a control study to see what the effect of lampoon quantitatively is. So we hypothesized that lampoon would decrease the LVOT velocity because it increased the area for flow and reduce the pressure gradient in patients undergoing lampoon. So we took patients that actually got lampoon in an investigational device study at Emory, and who had acceptable CT quality afterwards, so we could actually identify the valve stats on the CT. So they did TMVR with the Lampoon, and then we did a computational fluid dynamics simulation from that. And that's the as-performed procedure, so that's exactly what happened to these people. Okay? Then we did TMVR without Lampoon and did computational fluid dynamics, and that's the virtual control. So we reverse engineered it, like they didn't do it. Okay? We compared the hemodynamics. So in essence, we had the as-performed procedure with the holes exposed in the valve, and then we covered them up in the geometry, and then we did the simulation that way. So if you came to this talk hoping to see state-of-the-art fluid-solid interaction model, you came to the wrong talk. Okay? So we did, I'm an imaging guy, we did the contrast-enhanced ECG-gated CTs, did the segmentation. We got the inflow conditions from the flow that we could calculate by the volume change in the CT over the cardiac cycle, and we did a steady flow rigid wall simulation. And that's because we want to get feedback right away as to what this does for cases in the future. So what we look at, we looked at peak velocity, we looked at pressure gradient, and we looked at effective orifice area, which is usually used in the aortic side, but we just applied it to this side as well. So just sort of taking a look at the stream lines and stream traces. If you look at this, you'll see that there's actually, as you would imagine, there's flow through these open valves, okay? And the virtual control, so when we cover them up, right, you get the neo-LVOT now has much higher velocity through it as you go through. So increased velocity is obvious from this because the area changed when we expose those cells. Right? So this is just another case where you can sort of look at it from without Lampoon, virtual control on the left. You see the higher velocities, and you see the exposed cells versus the closed cells. And then you see the flow going around the valve in different ways without Lampoon, but going through the cells, and so you got lower velocity in the Lampoon case. So as far as quantitative results, in all the subjects, the peak velocity was reduced. So each one of these had their own specific one. It's not, we identified how many holes were open, okay? I didn't put that data on there, but it was about 2 plus or minus 1 holes were open. So some people had 1 hole open or half hole open, somebody had 2.5 or 3 holes open in the stent, depending on their geometry. But in all of them, the velocity, peak velocity decreased and the effective orifice area increased, and those were significant values. So I plotted the pressure gradient a little different way. Actually, I shouldn't say I did, Kesha plotted it. Okay. And so this was so now we have different subjects going from the smallest neo-LVOT area at the CT that was the screening CT and going to the right. And then TMVR without Lampoon, which is the virtual control, is in red. So you see in each one of them, right, there's a decrease in the pressure gradient, okay, with every one of these. But as we get down to the end, the effect is actually pretty small. So what you see from this is really this Lampoon effect is important in people with very small neo-LVOTs who have a chance of having a big gradient. So conclusion, we performed an in silico study which assessed hemodynamic impact of Lampoon quantitatively, which could not be done in a clinical trial in any way. And it seems to show us that it leads to consistent improvement in hemodynamics for TMVR and supports as a strategy to mitigate LVOT obstruction. So this was just published in Frontiers about a week ago, and I just wanted to say thanks to the American Heart Association for getting Kesha a fellowship. Okay? So I'm just going to leave this slide up for questions as to sort of how we look at this happening in the future.
valves are exposed, how likely is it going to fly off or actually clog and throw in systemic circulation?
Right, so they haven't had any of those cases. That was part of the IV trial, but there is definitely evidence of hemolysis and bleeding from this, okay? But not adverse events at this point in time. So I think as it becomes more widespread and potentially gets into the hands of other people, there's not saying exactly with it. So, yeah. It's definitely a crazy thing.
Have you had any investigation of the regulatory rates after the propagation of this valve? Because most of you are confident the bullshit stress correlation. For example, this kind of data is the correlation would be
Right. Yeah, I think there's definitely room for a lot more, but since this was like a really crude sort of steady flow thing, I'm a little worried about reading too much into some of the wall shear stress. One thing I'll sort of make a comment in is that this is really dependent on where the valve is put in, right? So if the valve is put in higher or lower, then that's going to really affect the size of that VOL-VOT. So that's really, I think, a study that we need to sort of take a look at, and valve profile as well.
Dr. Tritsky, does since you said that for the large neo-LVOT, the effect is really small, does that indicate that maybe lampoon wouldn't be necessary and that we can save it for the patients with those larger?
Yeah, and this really is a really good point. So what he's saying is if you look at those neo-LVOT numbers, they're basically like, why did you do lampoon on those people? Because if you know what the threshold value is, they were actually over the threshold value. However, this gets to where the valve gets implanted. So when they thought it might go in to cause that, but then it really didn't. It was really implanted higher. So that piece is something in the planning that's really sort of not specific.
All right. Thank you very much.
Right.
Our last speaker of the session is Yoganathan from the Eastern Group. He'll be talking about toward subject-specific understanding of the right non-coronary bicuspid aortic valve association with molecular gene expression.
All right, thank you. So let's start with the non-rated aortic valve, which consists of three different cusps named the left coronary, right coronary, and non-coronary cusps. And these cusps open and close, maintain forward blood flow from the left ventricle into the aorta. Its function is very physically demanding in nature because during systole, the cusps need to open with a really wide orifice area to allow blood to flow through and essentially through across the valve. And then during diastole, the cusps must press together, create a tight seal, prevent regurgitation during a period of high back pressure on the valve. And as a result, the cusps are constantly undergoing a range of different hemodynamic stresses. First, we often think about wall shear stress, and this is really side-specific. So while the ventricular side is often exposed to high magnitude unidirectional wall shear stress, the aortic side is often exposed to low magnitude oscillatory wall shear stress. The valve is also subjected to pressure-induced stresses like bending stresses, and mainly occur during diastole and act perpendicularly to the valve surface. This further leads to an elongating type tensile stress on the ventricular surface and a shortening type compressive stress on the aortic side of the valve surface. In short, these mechanical stresses can all contribute to mechanical deformations in the form of stretch and strain. And it's important to reiterate that each side of the valve is exposed to different types of mechanical stresses, and this becomes relevant in terms of disease pathogenesis. So the valve is able to withstand all of the everyday wear of mechanical stress through constant renewal and maintenance of this extracellular matrix. And the important thing to note from this slide is that the ECM is synthesized by a population of valve interstitial cells shown in orange. And these are normally in a quiescent, inactivated state in a healthy valve. And then lining valve cusps are a layer of mechanosensitive valve endothelial cells, which can sense mechanical stimuli in the environment and relay molecularly with the VICs to regulate their phenotype. However, imbalance of these components can lead to valvular disease such as calcification, for which the underlying mechanisms are largely unknown. But we do know that the valve interstitial cells become activated and take on a bone-like phenotype, mainly in the setting of inflammation, endothelial dysfunction, and extracellular matrix remodeling. By end stage, there's the formation of really stiff calcific nodules, mainly on the aortic side of the cusp, that further restrict the mobility of the valve and lead to aortic stenosis. And relative to our work, mechanical stress is often thought to be a key contributor to this disease process. Specifically, it's thought that physiologic mechanical stress is actually needed to maintain the normal VIC phenotype, whereas altered mechanical stress can promote procalcific mechanisms such as the ones I've listed above. And this really becomes important when we talk about bicuspid aortic valve, which results from the fusion between 2 of 3 cusps during embryonic development. And while there's many different configurations, the 2 most common are the right-left and right non-coronary configurations. And importantly, whereas calcification typically occurs in the tricuspid population at around age 65, over 50% of young adults with BAV will develop premature calcification at the age of 35. And it's more severe in the right non-coronary configuration. And while the cause of premature calcification of BAV is not known, we do think there's evidence to suggest that altered mechanical stress could be the key pathogenic contributor. And we believe this to be a key mechanism because several computational, in vitro, and clinical studies have all corroborated the common features of BAV, such as the smaller orifice area that's more elliptical in shape, which skews blood flow towards the non-fused cusp and impinging on the wall of the aorta. However, the majority of these studies have mainly focused on the adult population after the onset of calcification has already occurred. And additionally, the mechanobiology studies haven't yet found a direct link between the wall shear stress and mechanical stresses and downstream molecular changes involved in calcification. So to address this goal, our goal of this project is really twofold. First, we want to look at mechanical stresses in BAV patients over time, and specifically before the age of 35 when they typically develop calcification. What we're also really hoping to do is then associate these regional mechanical stresses with different molecular markers for calcification, and this will hopefully answer our questions surrounding why some regions of the valve cusps, such as the fibrosa or aortic side or the fused region of the valve, are more prone to calcification. And so to assess the mechanical stresses in BAV over time, we've been working on a robust fluid structure interaction simulation protocol, and one that tries to build upon previous models and aiming to advance our capability more closely replicating physiologic conditions. So for this, we've been working with a 23-year-old patient with right non-coronary BAV and age-matched tricuspid aortic valve control. So working from the MRI imaging, this allowed us to create a 3D reconstruction of the aortic root, sending aorta and coronary arteries into vascular. And then next, we created the valve cusps in SolidWorks using relationships of valve dimensions reported in literature, but that were made patient-specific to the geometry. And then the opening and closing behavior of the cusps is then validated using a series of metrics like geometric orifice area, effective orifice area, and the transvalvular pressure and velocity gradients. And then to replicate the physiologic flow and pressure conditions, we impose a left ventricular pressure waveform made patient-specific based on their reported blood pressures in clinic, as well as the inflow data from phase contrast MRI imaging. And then at the aortic outlet, we impose a Hessel model to represent downstream systemic resistance. And additionally, our model accounts for coronary flow, which is important because coronary flow conditions can affect the flow in cusp sinuses and ultimately along the cusp surface. Implementation of realistic material properties of human valve cusps in FSI simulations is pretty active area of research, but we're limited currently by the availability of valve tissue from younger patients that are both healthy and, for that matter, with BAV. So oftentimes, FSI simulations rely on mechanical properties from much older disease cusps, which are often much stiffer. But in our model, we're actively working on implementing biomechanical properties from patients in the age range closer to our test subjects to better replicate the biomechanical nature of the valves. So what I'm showing here is biaxial tensile testing data from a 20-year-old human healthy donor, and then alongside a fit to the gastric occult skull model, which was originally adapted to arterial modeling, but can be adapted to develop custom material properties. And so from these simulations, we can look at a whole range of different mechanical stress indices, and what I'm showing are very preliminary results prior to our ongoing fluid mesh convergence studies that we have going on currently. So if we're looking at instantaneous wall shear stress at peak systole, I'm showing here the normal tricuspid aortic valve case with the bicuspid aortic valve case. And just for the sake of this presentation, I've shown simple fusion between the two cusps in the same geometry and same boundary conditions. We can see that it elicits the same elliptical valve orifice area that we expect to see in the bicuspid aortic case. But just when keeping everything else constant, but simply fusing the two cusps together, we can see some slight differences already occurring in the wall shear stress on the fibrosis surface, meaning that it's a higher magnitude is extending down further into the belly of the leaflet region. We also looked at von Mises stress at peak systole, which again can show us the different regional differences in the two cases. Specifically, where the fused region is here, there's kind of a juxtaposition of a region of very low von Mises stress with regions of very high concentrated von Mises stress. And this is kind of the part where we want to focus on, is looking at the key differences between the cusps and trying to figure out where are the differences and how do they relate to the regions that get commonly hit with calcification in this population. So once this pipeline that we're kind of optimizing currently for our test subjects in the young adult age group is completed, we will be able to extend our analysis in a temporal manner to track the evolution of mechanical stress over time in the bicuspid population. And we believe that this will shed light on kind of the mechanisms leading up to calcification rather than after. However, this is not possible in humans to track molecular changes in the valve tissue over time occurring in response to the mechanical environment. So to complement our human studies, we've been working with a BAV mouse model that within the same genotype either develops a healthy tricuspid aortic valve or a bicuspid aortic valve with premature calcification. So we can use this model to better isolate some of the molecular changes that are occurring in response to the mechanical environment without the genotype as a variable. And our long-term goal is to perform FSI simulations to characterize the mechanical environment, which will then correlate with differential gene expression to further tease out mechanically driven mechanisms leading to BAV calcification. So to do this, we've been using echocardiography and 4D flow MRI, which first allows us to assess the cardiac function in this mouse model, but second provides us the necessary parameters for building a computational model. In parallel, we will perform molecular studies to examine gene expression in response to the mechanical environment. And though we are in the early phases of this kind of characterization of our BAV mouse model, our echocardiography data suggests so far that the classic BAV cases in our mouse model undergo a similar progression of key hemodynamic metrics, making it a reasonable model to study human BAV disease mechanically. And like I mentioned earlier, the healthy disease phenotype in light blue, or the healthy genotype in light blue, develops a tricuspid aortic valve 100% of the time, whereas the disease phenotype in dark blue either develops a bicuspid or a tricuspid aortic valve. And so we have encountered at least one BAV case in this cohort of BAV mice, and within the span of 5 weeks, we've seen that it's progressed from a peak aortic velocity of almost 2,000 per second. And while the data shown now is not statistically significant, we expect there to be more difference when we yield more classic BAV cases and start to separate those from the normal tricuspid aortic valve cases in the same phenotype. Similarly, we've seen similar progression in peak aortic or peak pressure gradient, which in the classic BAV cases increases from 500 Hg to over 1600 Hg in the span of 5 weeks. So again, we think this would be a good mouse model to examine mechanically driven mechanisms that are also present. Again, we're also optimizing 40 flow MRI protocol that we think will be able to provide the necessary material property or boundary conditions for building a And then from this, we in tandem will correlate these different mechanical stress indices that we get along the valve cusp, really try to tease out some of the molecular markers for constipation that are changing in response to mechanical environment, specifically BAVs. So to conclude, we believe that examining mechanical stress in young patients will shed light on mechanisms leading up to the calcification onset in these patient subgroups. We also believe that by doing these studies with BAV mouse model will not only validate the mouse model for future study of human BAV disease, but it also provide insight into the molecular gene expression changes that occur in response to the BAV mechanical environment. With that, I'd just like to thank the Lincoln Lab and all of our collaborators that are helping us optimize the protocols, and I'll be happy to take any questions or feedback on our project. Yes. That's from a normal tricuspid aortic palpitation. Not that we are aware of. And in terms of the BAV kind of properties that we're planning to include, from our Heart Institute that were part of keeps resected tissue from BAV cases, so we plan to possibly include those requirements. Yes. We're now focusing on specifically the valve and calcification that are valve, but I guess ideally in the future we could expand that to